Okay, now we're going to see angles measured by two different units. One's in degrees, the other is in radians. This is the unit circle. We have learnt that angle is measured from this east line and we go anti-clockwise. So 0, 1 is 90 degrees from the starting point 1, 0. We split it into quadrants, 1, 2, 3, 4. So this up here is 90 degrees, this is 180 degrees, 270, and then back to the start, 360 degrees. Let's to define the radian unit, we're going to use 360 degrees right around to the start like that. Now 360 degrees is equivalent to travelling around the outside a full circumference. Now if you can remember from previous years, the circumference of a circle is 2 pi r, and it's simply, that's the definition of a radian, is that 360 degrees is equal to 2 pi radians. Now it's 2 pi r is the distance around the outside. If you take the r out and make it radians, then it's independent of the size of the circle. No matter what the radius is, it's always going to be 2 pi radians around the outside. To bring this down to the definition of what 1 radian is, then we just have to use fractions, proportionality. What you do to this side, to get to 1, we're going to divide by 2 pi. And we got to do the same to the other side, divide by 2 pi. This is just simple ratio technique. Now if you do 360 in your calculator and you divide it by 2 pi, then you'll get 57.3 degrees. So that's what 1 radian is equivalent to. It's independent of the radius, it's just another measure of angles. Now to see that in the textbook, it says that 1 radian is the angle swept out by 1 radius unit around a circle, and is approximately 57.3 degrees. You can see that it's independent of the size of the circle. If we had 1 centimetre here, then it's 1 centimetre around here, because that's equivalent to a radius unit. If you had 2 centimetres along here, then you've got 2 centimetres along here. That's equivalent to, once again, 1 radius unit. And if you've got 3 centimetres, this is 3 centimetres, it's still 1 radius unit. So we say that this is all 1 radian, because we've got radius, radius, radius. Okay, now another way of converting it is to use a flow chart, which is down here. If you want to convert degrees to radians, then you times by pi on 180. If you want to go from radians to degrees, you times by 180 on pi. So I'll go back to my Word document and illustrate that. So using that conversion chart, we can do this another way. We can start off with 360 degrees, and we're going to multiply by pi on 180. Now 360 divided by 180 is equal to 2, so we end up with 2 pi, and that's exactly what we got up here, and we're getting the same answer. So the conversion chart agrees with this concept of the circumference, and you can do that for any angle. So for example, let's try and complete this now for all of them. I'll bring up the unit circle, and I want you to see if you can actually get the radians for each of these angles around the unit circle. So I'll do the first couple. The first one we've already done 360 degrees, that is equivalent to 2 pi. Let's do 90 degrees. To do the 90 degree case, you will get the degrees and you times by pi on 180, and so 90 into 180 goes 2, so that's pi on 2. So this is pi on 2 for 90 degrees. You can do other multiples of 30 or 45. Let's do, say, 30 degrees, this one here. That will be 30 times by pi on 180, and 30 goes into 186 times, so that is equivalent to pi on 6. 30 degrees is the same as pi on 6 radians. Now pause the video and see if you can do all of these angles around the whole unit circle. And here are the answers for degrees and radians around the whole unit circle. You could have done this using fractions. I'll show you. So we did a pi on 6 for this one here. This angle was pi on 6. Notice the next multiple of 30 is 60, and it's double it. So it'll be 2 pi on 6. So this is 1 pi on 6. This here is 2 pi on 6, because that cancelled down is really pi on 3. So that's your next multiple of 30. Your next multiple of 30 is 90, which is 3 pi on 6. And then the next one after that is your 120, which is going to be 4 pi on 6. Notice that cancels down to be 2 pi on 3. And you could go through quickly doing that all around the circle. Rather than start counting 1, 2, 3 all the way around to 12 pi on 6, you can always go backwards. So let's say we wanted to work out why it was 11 pi on 6 here. It's actually 2 pi, going clockwise is minus, so it'll be 2 pi minus pi on 6, it's 30 degrees the other way. And to work that out, well, 2 pi is the same as 12 pi on 6, and 12 pi on 6 take pi on 6 is equal to 11 pi on 6, which is what we have here. So there's other ways of doing it than using that conversion chart, which is times pi on 180. Likewise, you can do that for all the multiples of 60 and multiples of 45. Just quickly showing you the multiples of 45, because that's pretty simple. It goes 1 pi on 4, 2 pi on 4, 3 pi on 4, 4 pi on 4, 5 pi on 4, 6 pi on 4, 7 pi on 4, 8 pi on 4, and that's all the multiples of 45. Now I'll take this opportunity to introduce the calculator to show you that it can cope with radians and degrees. So let's take a random angle like 120 degrees, so this one along here. We can see that it's 2 pi on 3 and 120 degrees. So let's look at just the x coordinate, the cos value. We can see from here we should get minus a half for the cos of 120. So cos of 120 should be minus a half, and the cos of 2 pi and 3 should also be minus a half. Now we'll just see if the calculator can cope with these. So here is the calculator. We're going to put in, first of all, in degree mode, you have to click the mode, go down and lock it on degree. Press enter and then quit. Now if we put in the cos of 120 degrees, then we end up with minus a half, and that agrees. But if we now put in the cos and we put 2 pi on 3, divide 3, we actually get the wrong answer because we are in degree mode and we're using radians. So we have to go to mode, change it to radians, then quit. Do that again, so the second entry. So it's cos 2 pi and 3, press enter and it does work. So when you're in degrees, you've got to use degree mode. When you're in radians, you've got to use radian mode to get the right answer. Okay, so now we'll go back to the textbook and see that these questions here we've already covered. So converting radians, converting 2 radians from degrees, we've done that going around the whole unit circle. Likewise, you could go back the other way, this one here, from radians to degrees. If you wanted to practice that, I think it's pretty straightforward, but if you wanted to practice that, you could pause this, try some of those questions there. 1, 2, 3, 4, and if you come back and just have a look at the solutions. And here's the solutions here for 1, 2, 3 and 4. Okay, moving on to the identity. Now the identity is cos squared plus sine squared is 1. That's simply Pythagoras' rule. If you look at the unit circle, we have the x-coordinate is equivalent to cos theta. The y-coordinate is equivalent to sine theta. Now we know Pythagoras, the hypotenuse squared equals the square, sum of the squares of the two sides. So we're going to end up with this identity. Cos squared plus sine squared equals 1 squared, and 1 squared is 1. So you should really commit that to memory, because that's just simple Pythagoras. And we're going to use that in a lot of questions. Now it does say also to bear in mind that cos ranges between -1 and 1 and sine ranges between -1 and 1, which is obvious because we can't go any bigger than those values in the unit circle. We already know that positive is anti-clockwise. And we've already done a lot of these questions before. So we're going to do question 4 and 6. So using this identity, we'll do question 4, and this is trying to find cos theta given sine theta. Sine theta is a half. Question is, what is cos theta? Now we can use the identity, which is cos squared plus sine squared is equal to 1. Now sine squared theta is the same as sine theta all squared. So sine squared theta is the same as sine theta squared. That's a shorthand way of writing it, so you don't have to put brackets in. So we're going to put sine theta as a half into brackets and square it. So we've got cos squared plus a half squared equals 1. and we have to now solve for cos. So first thing is to square the half. So we'll have cos squared plus a quarter, because a half times a half is a quarter. Now we take a quarter over to the other side. So we have cos squared equals 1 minus a quarter. So cos squared equals 3/4. And now to get rid of the square, we square root. And when you square root, you'd have a plus or minus. So it's plus or minus root 3 on 4. Now, that's when you square root 3 on 4, that's the same as square rooting 3 and square rooting 4 separately. And we can square root 4 to get 2, so it's really plus or minus root 3 on 2. And that's the standard value we recognised from the unit circle that we did a while back. So we can actually illustrate the meaning of this, but with looking at the unit circle. They've said, what are the possible cos values when the sine value is a half? In the question, it said that the sine value has to be a half. Now the sine value is the y coordinate. So the y coordinate here is 1, half is there, so it is that point and that point. They are the 2 points we're talking about. What are the respective cos values, the x coordinates? Well, that will be, if we look at these 2 triangles, that'll be this one here, all the way over to there, and this one all the way over to there. Now we know that that coordinate there is minus root 3 on 2, comma, a half. This coordinate over here is plus root 3 on 2, comma, a half. So that is why we're getting 2 answers for the cos, because there's one on the left, which is the minus, and there's one on the right, which is the plus. And this represents the x coordinate, which 2 x coordinates, and this represents the y coordinate. Okay, so you try a similar thing for these, B, C, D, using the identity cos squared plus sine squared equals 1. So just pause that and come back for the solutions. And here are the solutions. We have for A, B, C, and D. Notice D is only giving one answer there. Now question 6, we just fill out this table here, reinforces terminology of interval notation that we did in the previous topic. First quadrant is between 0 and 90 degrees. That's this quadrant here. That's in degrees. We can actually do it in radians. We've learnt now the conversion chart. Instead of 90, we go pi and 2. Now here we want to say whether it's positive or negative. We can see it's going to have a positive x coordinate and a positive y coordinate, anything that is in this quadrant. So it's plus and plus. You try and fill out the remainder of that table and come back and have a look at the solutions. And here are the solutions. So quadrant 2, quadrant 3, quadrant 4. These are all the intervals in degrees and radians, and these are the signs of the cos and the sine values. Now to finish off, we can now do question 7, which includes the identity and the interval notation together. So I'll do the first one, where we've got cos theta equals 2/3, and we have to work out sine theta, but they give us a constraint, which is that theta has to be between 0 and pi on 2. In other words, we are in the first quadrant. Now once again we use the identity, which is cos squared plus sine squared equals 1. We know that cos is 2/3, so that's 2/3 squared plus sine squared equals 1. Now 2/3 squared is the same as 4 on 9. And now all we need to do is take the 4 and 9 over the other side to become minus 4 on 9. 1 minus 4 on 9 is equal to 5 on 9. And so now to get sine theta, we square root. Whenever you square root, you need to put plus and minus. And so we have square root of 5 on 9. Or you could call that plus or minus root 5 on root 9, and root 9 is 3, so it's plus or minus root 5 on 3. Now we've got two answers here. If we illustrate that on the unit circle, you can see that they are asking when cos theta is 2/3, that's the x coordinate, 2/3 is around about there. There are two values, there's this one here and this one here. Both of these have a cos value of 2/3. They both have the same x coordinate. And we found two values for sine theta, so we could say that the coordinate of that point is 2/3 comma plus root 5 on 3, and this one is 2/3 comma minus root 5 on 3. But they've given us a constraint that we have to be in the first quadrant. So they don't want us to give this point down here. So what we do is we end off by saying this: sine theta equals just the positive version, the positive root 5 on 3, and we give the reason because of this constraint that theta has to range between 0 and pi on 2. And that's how you do question 7. So if you have a go at the rest of those or some of those, then come back for the solutions. And here are the solutions for 7. We've got A, B, C, D, E and F